That one I don't know. For your professor. We'll get started in just a minute. I think I know a few more folks are stuck on the elevator because I just saw them 3 minutes ago. So wait for one more elevator load and then we'll get going. All right, we are going to get started. This is our final colloquium of the 24-25 school year. So thank you all so much for being here. Woo! It is my real pleasure to introduce our speaker today, Professor Sally Uwe. Professor Uwe did her PhD at the University of Arizona, followed by her postdoctoral work at Cambridge University, and then STSI. She was a staff astronomer at Lowell, and then she joined the University of Michigan as a professor and is now the Arthur F. Turneau Professor. And without further ado, I will just point out that she's done a number of incredible service, like community and boards. She is on the AAS board. She is on the Aura board, didn't want to get that wrong, and has done seminal work in massive star feedback. So please welcome our speaker.
Well, thank you so much, Shannon, for that kind introduction. And thank you all for having me. I've really enjoyed my time here today. So yeah, we're going to be talking about massive stars, and I do study massive star feedback. Today we're going to be studying massive stars in particular. This is work that I've been doing with my research group over a number of years, including a series of undergrads here, my graduate students, and here are just some of my more senior collaborators. So let me first describe what I mean by massive stars. I mean the massive stars that are actually going to be responsible for massive star feedback. And so there are two modes of massive star feedback that I really focus on, which are the mechanical feedback effects from massive stars that comes from their strong stellar winds and their supernova explosions. This seems to dominate at fairly high metallicity, around galactic type metallicities. And then there's also radiation. There's a lot of energy in the Lyman continuum and ultraviolet radiation that comes from these massive stars. And it turns out, a paper that I recently wrote with my undergrad, Michelle Jeckman, that at lower metallicity, since mechanical feedback tends to be suppressed, the radiation-dominated feedback takes over, at least for the first 10 million years. And I think we're only really starting to appreciate that now. So basically, these massive star feedback effects have fundamental impacts on galaxy evolution. There are these green key galaxies, these Wolf-Rayet galaxies, blue compact dwarfs, starburst galaxies, and maybe even little red dots, although my conversation with Mitch Spiegelman today is having me persuaded that maybe not, but they could be involved in these little red dots that have been recently discovered by JWST as another one of these kind of close to primordial type populations. So how do massive stars evolve? Clearly, The evolution of these massive stars is fundamental to understanding the kinds of feedback effects that I just mentioned, and especially the output of ionizing radiation. Well, massive star evolution has never been fully understood. I'm just showing you here a typical HR diagram, and we have the O and B stars that at least we think we kind of know and love along the main sequence. We also have a zoo of other types of massive stars, and their origins have always been a little more murky, and we know that those types of massive stars must be telling us something about massive star evolution. So we're hoping to maybe try to start teasing some of this apart. We have OBe stars. These are like OB stars, but they have an E for emission because they have Balmer line emission. We have Wolf-Rayet stars. Wolf-Rayet stars are extremely hot. We think that we're seeing the cores of some of these stars, or at least something close to their cores. So they're to the left of the main sequence. We have luminous blue variables. These are stars that are photometrically very variable. They can also show some spectroscopic variability. They have eruptions. They're a little bit more toward the red, but they are still blue stars. That's in their name. We have supergiant B bracket E stars. These are supergiant B stars, and they have forbidden emission. That's what the bracket line stands for. These are very strong, narrow emission lines, and they are B supergiants. And then we have, these aren't a spectral type, but they're kind of a category of stars that people have started just calling very massive stars, things that are at the top of the HR diagram, maybe 100 solar masses or so, things that are close to the Eddington limit. I'm not going to talk about red supergiants today, but of course they are another type of massive star. So how do we put the picture together with how these things evolve? In Astro 102, we basically show this picture and we say, okay, here is the evolution for single massive stars. They start on the main sequence and then they move to the right. They just evolve at kind of constant luminosity and then they blow up at some point. Well, it gets very complicated because we may actually be looking at binary stars, and that has turned out to be something that has emerged to be a real thing over the last 10 years or so. We have two stars, and when they start interacting with each other, we ultimately end up with a stripped star and a fast rotator, and it works like this with this lovely little cartoon made by Ilse Jotberg. So the more massive star starts to evolve, it bloats up, it fills its Roche lobe, and its companion, the mass gainer, starts spinning up. It becomes more massive, and now you have a stripped star here, which is a very, very hot star and could be seen as a Wolf-Rayet star. When you look at this on the HR diagram, it gets very complicated, very different from what I just showed you. So here's some models run by Pulse way back in 1994. We have a 16 solar mass star, a 13 solar mass star, both born at the same time on the main sequence at time A. At time B, then we have the more massive star filling its Roche lobe, and it becomes the mass donor. The lower mass star becomes the mass gainer. It becomes more massive. It gains luminosity disproportionately, maybe even by a factor of 10, as we see in this plot right here. And so the lower mass star ends up way up here and starts evolving out here. What was the higher mass star evolves at lower luminosity than we would have expected. It has a lot of its mass stripped off, and so it ends up way over here on the left side of the HR diagram, probably becoming some type of Wolf-Rayet star or something super hot. This one, in principle, could also end up on this side if, so this one blows up. This one now could be donating its mass to the neutron star if it fills its Roche lobe. So maybe it would also end up over here by the time it blows up. So very complicated. And so how can we really start understanding how this all works? And as mentioned, this is all very important for what happens to which stars become FUV bright, which means that they could be producing Lyman continuum radiation. And at low metallicity, even if a star is just rotating very fast, like we saw the mass gainer do, supposing it had just always been a fast rotator, it could, even just by virtue of that fact, evolve off to the hot side of the main sequence. And this would be more expected to happen at low metallicity. So at low metallicity, we have more binaries. more and faster rotators, and we end up with these stripped stars as well. So it's believed that about 70% of the O and B stars at galactic metallicity will become mass transfer binaries at some point in their lives. And we believe that there are even more of these at low metallicity. Basically, people think that 100% of the massive stars are mass transfer binaries at some point at low metallicity. And so obviously this has profound consequences for massive star evolution, feedback, Lyman continuum production, and also for the descendant phenomena of these two stars. We could produce gravitational wave progenitors. We could produce high mass X-ray binaries, gamma ray bursters, various different kinds of core collapse supernovae. And basically, this whole new world of transients and multi-messenger astronomy is very much based in an origin here from these massive binaries. So we need some more observational evidence that we can bring to bear to try to understand how binarity affects massive stars. And one thing that is very helpful is the fact that binarity often leads to acceleration of the stars. So for example, on the right-hand side here, you can see the supernova ejection mechanism, where if you have a tight binary that's bound, eventually the more massive star will blow up, and then it could eject the second star as an unbound object. It could also give that second star a kick. So whether or not the system becomes bound or unbound, it becomes a runaway, or at least it becomes accelerated, and it may become ejected from its parent cluster. I generally use a definition of ejected from cluster, i.e. unbound from cluster, and going slower than 30 kilometers per second as a walkaway star. But anyway, we don't need to get into that detail. There's another mechanism, which is the dynamical ejection mechanism, where you just have a lot of stars interacting in a dense cluster core, and then just through these different gravitational encounters that you get, then you can also eject the stars that way. And you could also, as you just saw here, eject a binary system. If we watch this again, you'll see it happening. So there goes the binary system. So you could have a pre-supernova binary system ejected, in which case you then end up with what's called the two-step ejection mechanism. This was suggested first by Flum, Altenburg, and Krupa. And so the surviving star there gets doubly accelerated and is going even faster than before. So if we have all these ejected stars, that means that the field must have a population of these massive stars that have been accelerated. So we decided to leverage this survey that we had done a long time ago with my graduate student Joel Lamb to look at the field O and B stars and see what evidence of binarity we could maybe obtain from these data. So this is the runaways and isolated O-type star spectroscopic survey of the SMC. RIOTS-4 is the acronym, and this is a sample of stars that was photometrically selected based on this work by Uwe, King, and Parker, Joel Parker being in the audience here. And the field stars are defined to be objects that are at least 28 parsecs away from another O and B star in the samples. This is a fairly deep field sample. And we obtained spectra of all these objects. They constitute about 25% of all the OB stars in the SMC. So the first thing to do is evaluate how many of these stars we think were actually ejected versus actually perhaps forming as field stars. Well, to first order, you'd think that wouldn't happen, but you never know. So my student Irene Vargas Salazar had looked at this, and she basically tried to evaluate whether any of these massive stars could actually form by themselves, more or less, by searching for low mass companions around them, because the IMF tells you that you have to form little stars along with big stars. So if these stars formed in relative isolation, you hopefully should see the little companions. So she used the Ogle survey to do that, looking down to magnitude 19 to see if she could find tiny stars in the neighborhood. And here's an example of where she did find one. But she didn't find very many. So even though she used 3 different methods to try to evaluate this, the friends of friends, the nearest neighbors method, and she stacked the fields for basically all of the objects in the sample, the best that we could do was estimate that about 5% of them, maybe at most, could have formed in relative isolation, which is still a very interesting number because it does seem to be non-zero. It might not be non-zero, but it seems like it's non-zero, and we have other evidence to suggest that as well. So that's a separate problem for massive star formation theories, actually. But we can be reasonably confident that at least in the SMC, 95% or more of the stars are indeed ejected from clusters. So this can help us try to learn more, perhaps, then about the link to binarity. So one interesting thing that emerged from the survey is that about 1/3 of the stars, or even more, turned out to be these OBe stars, stars that actually show Balmer emission. And you can see that right here in H beta and over here in H gamma. So where does that emission come from? It comes from what's called a decretion disk. I always think that decrete is a strange verb, but these decretion disks are believed to form because these stars are spinning so fast that essentially they're near breakup and they actually manage to spin out this small circumstellar disk. So one other thing that we noticed in the SMC, having detected that many of these classical OBe stars, is that indeed they seem to go to earlier types than we had expected. So in the galaxy, the earliest spectral type for the OE stars is 07.5. Whereas in the SMC, we found 9 stars that were actually earlier than that, and they went all the way to the earliest type that one could even basically see, something like 03 stars or something like that. Additionally, we found 29 OE stars total in the sample, constituting 25% of all the field O stars in the SMC. Whereas in the Milky Way, the OE stars are less than 10% of the known O stars in the galaxy. So again, we're seeing more of these at low metallicity and going to earlier spectral types. So we might therefore conjecture that these little decretion disks could have come from mass transfer in a binary system, right? So if the OE stars are the mass gainers and their companion might have exploded previously, then they might have been ejected into the field. And so here's a plot from my former undergrad, Matt Dallas, where you can almost visually see that, right? The OE stars, the OBe stars are in red, the OB stars are in blue, and you can kind of see that the red stars do look more dispersed than the normal OB stars. And we can certainly quantify that. So this plot is a technique that's been pioneered by Smith and Tombleson. What we're looking at is the cumulative distribution function of the distance of each star from its nearest O star. O stars are kind of a proxy for where the clusters are located, right? O stars aren't supposed to travel very much because they have such short lives. So if you look at the distance to the nearest O star, you're kind of looking at the distance to the nearest massive star cluster. So we've got a variety of curves here, but these solid lines are the normal stars, and the classical OBe stars are in the dash, in the sort of dotted-ish lines here. So we see that the OE stars are in the sort of purple one here, and that the BE stars are in the dashed red lines here. And then we see the solid O stars are in this solid line and this solid line. And then we see that the B stars, normal B stars, are in this red line right here. So we do see, first of all, that the OBe stars are further to the right, meaning that the projected distance to the nearest O star is farther for the OBe stars than for the normal O and B stars. So it confirms our visual impression that they're farther into the field. Secondly, one thing to note is that there was a big difference between the O stars, the normal O stars, and the normal B stars. That makes sense because B stars have longer lives. The B stars have longer lives, they have more time to travel, and so you'd expect them to be farther out into the field. We don't see that with the OE stars and the BE stars, right? Here we see the O stars, the OE stars, and the BE stars are practically on top of each other. So that might also make sense if indeed the OBE stars are mass gainers, because they're mass gaining from their companions some arbitrary amount, and they've kind of forgotten what their original mass was, right? So it makes sense that they would not have as big of a separation as you would expect just from their lifetimes, because they've kind of changed the lifetime that they should be inferred to have. And then thirdly, one thing to note here is the yellow line corresponds to the high mass X-ray binaries. So in a high mass X-ray binary, you have a neutron star. That means the companion has exploded. It's got a massive companion. And so these are clearly, indisputably, the objects that you would expect to have the supernova acceleration mechanism. So again, we see that the OBE stars, which are in the dotted lines here, are pretty similar to the yellow line, which is the high mass X-ray binaries. So it all seems to hang together pretty nicely that these OBE stars are indeed the products of supernova ejections. They're more isolated than the OB stars. They match the degree of isolation for the high mass X-ray binaries, which we know are supernova accelerated. And then the OE distribution spatially and the BE distribution seem to be pretty similar, suggesting that they have forgotten their original masses, which can be attributed to mass transfer in a binary system. So that's pretty nice. Well, if that's the case, then we should expect to see that they are indeed moving like ejected stars. And this is where the Gaia satellite really came in handy. So when we found out that there was going to be this Gaia data release, my former undergrad, Johnny Dorigo Jones, was ready to pounce on the data and calculate what the velocities of these stars were in their actual proper motions, which is, to me, mind-blowing, because we're looking at stars in another galaxy here. Here's a plot that Johnny made showing the actual vectors from the Gaia data. What we're doing here is looking at the proper motions relative to the local velocity field within 5 arc minutes for each target star. So we basically look at all of the stars within 5 arc minutes down to, it varies on which study we did, but something like magnitude 17 or 18 or something like that. And then we calculate the difference of the target star from that local velocity field. And we can also start seeing if maybe we see a difference between the dynamical ejection mechanism and the supernova ejection mechanism. The dynamical ejection mechanism predicts that there should be faster and more massive stars, and that the velocity is independent of the stellar mass. Whereas for the supernova ejection, we expect to see slower and lower mass stars, and that the higher mass stars tend to be slower than the lower mass stars. So here are velocity distributions for the OE, the OBE stars versus the OB stars. You can kind of ignore this one. This is everything here. And this is work that Johnny had pioneered, but this is updated now by my undergraduate, Grant Phillips. The OBE stars are shown in green, and they show a nice monotonically decreasing distribution and velocities. The OB stars are shown in brown here, and they show a somewhat more complicated velocity distribution that goes to higher values. So that seems consistent, first of all, with the idea that maybe the OBE stars are dominated by supernova ejections, which you expect to be a bit slower, and that the OBE and that the normal OB stars are maybe dominated by the dynamical ejection process, which tends to go somewhat faster. Now let's zoom in on these small distributions down here. So this is a zoom of these guys down here. So what we're looking at with the hashed plotted histograms are the pre-supernova binaries that are out there in the field. These have been ejected by the dynamical process, right? They have to be ejected by the dynamical process if they're binaries. They're pre-supernova binaries. They're eclipsing binaries and double-line spectroscopic binaries. Whereas the aqua, or cyan here, is plotting the high mass X-ray binary distribution, which, as mentioned before, we know are the post-supernova binaries. And so these seem to show the same kinds of patterns that we saw for the OBEs in green and the OBs in brown. We see that the high mass X-ray binaries seem to show a somewhat slower distribution than the pre-supernova binaries that we see over here. So that again seems to support the idea that the normal OB stars may be more dominated by dynamical ejections and that the OBe stars are dominated by the supernova ejections. One other thing to note is the structure that you see in the OB distribution. OB stars, if they're ejected dynamically, you would have a lot of different things going on. You could have ejections from binary systems. You could have ejections from triple systems. You could have binaries ejected. You could have single stars ejected and so forth. So it's not too surprising that we see more structure in the dynamical ejection distribution. Here we see something similar, but on the y-axis we now have the mass of the star. And again, the dynamical ejection scenario predicted faster and more massive stars. And so we see that this distribution is a little bit more shifted to the upper right when you contrast it with the OBe stars, which are slower and lower mass stars, which are shifted a little bit more to the lower left. These symbols that are overplotted are, again, the same tracer populations that we looked at before. The non-compact binaries are in the triangles here and diamonds, and they overlay these populations quite nicely. And same thing on the right-hand side with the high-mass X-ray binaries. So one thing to keep in mind is that the two-step ejections will look like the OBe stars because they're post-supernova objects, right? And so we see that there are, in fact, a few of these very high-velocity OBe stars. And so potentially, actually, they're not even showing up there. There are actually a few up in here, which are probably the two-step ejections. So we are actually seeing all three of these right now. One other thing that we can do with all this is, therefore, to look at the relative contributions from these two different mechanisms. Take this with a huge grain of salt, but basically we're seeing that the dynamical and supernova ejections mechanisms both contribute relatively equally, at least right now in these data, and that a lot of these dynamical ejections are pre-supernova binaries. For the supernova ejections, a significant fraction of them may be two-step ejections. But one thing to keep in mind is that all of this, which is also model-based, all of this depends upon assuming that these are a single stellar population, which clearly they're not. The SMC has a lot of different star-forming regions, and that's not accounted for in here. But the exercise in doing this shows you that the kind of approach that we're doing seems to hang together and therefore gives credibility to the interpretation that we've got here. One other thing that you can do is also probe the binary parameters in your initial conditions for the binaries in your model. So these are n-body simulations by O and Krupa that are plotted over here. And I've highlighted the parameter space that you've got plotted by our data over here. So if you just kind of look at the parameter space here and here, you can see that this plot, the data, seem to more closely match this than this. And the top plot gives you a uniform mass ratios for your binaries, whereas the bottom gives random pairings for your mass ratios of your binaries. And so already we're kind of seeing that the data seem to be favoring the uniform mass ratios. That's the sort of thing that we can be doing with this. Let's take a closer look at the binaries themselves. My student Irene Vargas Salazar, who recently defended her thesis, has been doing a radial velocity survey of just the wing section of the SMC. This is 50-some stars, I believe. And she has identified some radial velocity binaries, or at least objects that show radial velocity variability. And one thing that we can try to do is get a bit of a handle on the eccentricities of these systems by plotting the maximum change in radial velocity over 10 days on the y-axis versus the total change in radial velocity over the entire survey time scale, which is something like 2 to 3 years. And that's shown on the x-axis. So when you see those two values pretty much equal to each other, as we see for the OB stars, it's suggesting that you're seeing objects that are basically in circular orbits. and the further up you go, the tighter the orbits are. Notice that we have quite a contrast between the OB stars and the OBe stars. So for the OBe stars, we don't see that. We instead see that they tend to go toward larger values for the total change in RV rather than the short period. And so that tends to suggest that you may have eccentric orbits. It's not really changing a lot on small time scales, but then sooner or later you see the thing go around the corner. Again, this is all kind of statistical, right? But it's quite suggestive. One other big caveat that the referee has pointed out to us is that it's very difficult to measure the RVs of OBe stars because there is variability in the line profiles. We still feel reasonably confident about what we're seeing, but we definitely do need to take all this with a grain of salt. That said, you can compare this with binary population synthesis models from BPAS. And qualitatively, at least, the results are similar to what one might expect. What's being plotted here is not exactly the same parameters as what we have in the data. Basically, the data, these are binary population synthesis models using a sort of default BPAS population, which includes eccentricity distributions. And so the x-axis gives you the maximum change in the RV that you would expect in the total RV of any given object, any given system. And then the y-axis gives you the maximum change in RV if you had circularized that orbit. So it's the same energy, but it's a different orbital shape. So those are slightly different parameters, but they're clearly related to the kind of data that we're plotting here. And you can see that qualitatively, the behavior is very similar. So that again gives us more confidence that what we're seeing is real because it's actually predicted. One other thing we can do with the binary population synthesis models is see if we're actually getting any black holes. So looking at the OBe objects in particular, we can only get some lower limits on some of these orbital parameters. These blue squares are the high mass X-ray binaries, so they're well constrained and they fall nicely in this blob, which is the neutron stars. The M2 is the remnants mass, M1 is the observed stars mass. And so for these two objects right here, you can see they're well into the black hole range. I think the neutron star limit is somewhere in this valley right here. And then this object also is a very interesting star that we've written a separate paper about, AZV493. And so as a lower limit, by the time this actually hits the contours, you're again well into the black hole regime. So that's just something fun also to come out of her work, that we have a couple good candidates that we might want to follow up on. All right, so those are the OB and OBe stars. How about the other types of massive star classes? So luminous blue variables and supergiant B bracket E stars. These are kind of esoteric. The LBVs are known for having eruptions. They're very variable. They're near the Eddington limit. They're believed to be very dusty. You see a lot of infrared emission from them. The supergiant B bracket E stars are often associated with LBVs, but they do seem to be a distinct class. They have very dense, dusty disks. They are B supergiants, and they also are usually seen with circumstellar dust and gas. In both cases, it's always kind of been unclear what relation these types of stars have to being binaries or not. So we're going to take a look at their kinematics to see if that will help. This first is an example spectrum of a supergiant B bracket E star, and LBVs also look spectroscopically similar to these. These are just a plethora of narrow emission lines from the circumstellar material around them, usually from low ionization species like iron 2. And in the case of B bracket E stars, forbidden iron 2 is also seen. We also have a P Cygni profile that you can see there in, looks like H gamma. So here is from the work of Smith and Tomlinson, again, the cumulative distribution function of distances from the nearest O stars. So we're looking at how far into the field these different types of stars are. And they noticed that LBVs and supergiant B bracket E stars are among the deepest into the field of any population that they'd looked at. So that does seem to suggest that these stars, in fact, may have been ejected, whether as runaways or walkaways. So taking a look now at the velocity distributions, this is work done by my former undergrad, Julian DeMann. We're here looking at all of the LBVs in the LMC, not just the field stars, but all of them for which we could get good Gaia data, which is the vast majority of them. And so work by Aliozzo had recently classified these LBVs into two different kinds. Class 1 are objects that have dusty nebulae, sort of the canonical type, whether or not they have free excess. Class 2 are objects that apparently don't have these dusty nebulae. They do show free excess. And when we look at the velocity distributions of class 1 versus class 2, they're actually quite different from each other. So class 1, just look at them all together as a single distribution. They seem like they're runaways again. In contrast, class 2 don't seem like they're runaways. And then this guy's, probably a dynamical ejection. Everybody can be dynamically ejected, so these guys may be all just kind of dynamical ejections. But for the most part, it does appear that the LBVs without the dusty nebulae are not runaways, whereas the ones that do have dusty nebulae are. Yeah, kind of sounds like maybe the ones that have dusty nebulae have something to do with supernovae, and the dusty nebulae maybe have something to do with supernovae. That's kind of my thinking on that. But this also, I liked seeing that we had a class that was not runaways because it proved that we could actually find such a class, since many of these other classes have turned out to be runaways. We can now compare them to the OBe stars and the SMC that I showed you before. So this is looking at the LBV class 1 objects in the LMC and the OBe stars of the SMC. Remember that these guys were actually field stars. These guys are not necessarily field stars. So if you're missing the ones that are not in the field, then the OBe stars maybe need to have a sample that's at much lower velocities here. But generally, the shapes of these are pretty similar if you look at the class 1 versus the OBe stars, hinting that potentially the LBV stars may also be supernova ejections. They may have a distribution that's a little bit slower, and since LBV stars are much more massive than most other types, that may actually make sense in terms of supernova ejections. If we compare the supergiant B bracket E stars to the LBVs, we can also take a look at this. So the class 1 LBVs are now shown again in the orange with the hashes going in this direction. And then the supergiant B bracket E's are in red with the hashes going in the opposite direction. And so again, these don't look too dissimilar from each other. On the right-hand side, we're comparing the supergiant B bracket E stars with the OBe stars, and again, they also look pretty similar. You can basically take all of these, the red and the magenta, as a single distribution. They're just different types of supergiant B bracket E stars. We see that the supergiant B bracket E's have similar median velocities to this SMC field OBe stars, whereas the LBVs, again, are going substantially slower. The supergiant B bracket E's are lower mass in general, lower luminosity stars. So this, again, seems like it's reasonable if these are indeed supernova ejections. So here is that plot again of the cumulative distribution function of the distances from the nearest O stars. One thing that you do see is that the supergiant B bracket E's are farther into the field, significantly so than the LBVs. This is despite the fact, let's just say that the difference between how far they are into the field compared to the difference between their median velocities is greater. So their difference in median velocities was maybe 20%. And the distances between how far they are into the field is significantly greater than that, to the extent that it seems like the supergiant B bracket E's travel about twice as long in that state as the LBVs do, for what that's worth. This may have something to do with the longer lifetimes of supergiant B bracket E's, but it's pretty unclear. Okay, turning now to the Wolf-Rayet stars. These are objects that we think we understood for a while there. The classical model for the Wolf-Rayet stars was originated by Peter Conti right here in Boulder. The idea was that the different Wolf-Rayet classes, dominated by nitrogen, carbon, and oxygen, were an evolutionary sequence, that O stars would turn into WN stars as they blew away their own stellar wind, because they have these very strong stellar winds. They blew away their own atmosphere, gradually revealing the nitrogen-rich layer of the star, and then the carbon-rich layer of the star, and then the oxygen-rich layer of the star. There are also subclasses of these, the early type WNs, the late type WNs, which are cooler. Then you've got W and H stars, which show excessive hydrogen. Well, at least they show evidence of hydrogen in the first place. Let's just put it that way. There's also a new class of Wolf-Rayet stars called WN303 stars, which seem to have properties of both early type WNs and O3, normal O3 stars. And yet they have been shown quite conclusively to not be binary stars, not to be a composite class. They are actually a single type of Wolf-Rayet star. So basically, it turns out that there are more ways to create Wolf-Rayet stars now than the Conti scenario. The very massive stars themselves are objects that are near Eddington, and they are blowing away their own atmospheres under their own stellar winds with such force that essentially we're able to see deeper into the stellar layers, and they have very strong stellar wind signatures such that they may look like Wolf-Rayet stars. There's also, for almost as long as the Conti scenario has been around, the binary formation for Wolf-Rayet stars, where you have a binary system and the mass donor gets stripped, and that's the way that you get the envelope removed from the star so that it becomes a Wolf-Rayet star. And then, as I showed you earlier from the evolutionary tracks, if you have a very fast rotating star, just by virtue of it being that fast, it can actually evolve to hotter temperatures from the main sequence, and therefore emerge as something that may look like a Wolf-Rayet star as well. Something with exceedingly strong stellar winds, because its rotation makes it easier to be somewhat unbound. So the question is, how do these different subtypes actually map onto these mechanisms, if they even do? Karen Bjorkman has once said that the classical BE phenomenon was a symptom, not a disease. And it seems like Wolf-Rayet phenomena are in the same category. Here, just for those who aren't familiar, are spectra of two Wolf-Rayet stars, one from the nitrogen sequence and one from the carbon sequence. And you can see they're very easy to detect, very strong, broad emission lines. We see this in extragalactic situations as well. We have Wolf-Rayet galaxies and so forth. So they're a very important diagnostic of stellar populations, massive stellar populations at very large distances all the way across the universe. Okay, so here, this is not a PDF of the distances from the nearest O star, but rather of the velocities. So this is work that my undergrad, Caden Burkhardt, has put together. So this is the CDF for the velocities that we're measuring from Gaia, once again, for all of the Wolf-Rayet stars for which we can get good Gaia data in the LMC, once again. And once we are in regions that are pretty crowded, like the 30-door R136 cluster, we are missing some of those stars, right? Because we don't have good Gaia data in those circumstances. But for the most part, we have most of them. The situation where we are most biased in that sense is the O1F star / WN, which people often call just plain slash stars. These are sort of intermediate in spectral type between O supergiants and WN stars. And about 50% of these are in 30-door. So that means that we are biased more strongly to the field in this sample. And that's going to be important, as I shall point out. So let's look first at the subclasses that are associated with being potentially VMS stars, or in any case, very massive stars. So those are the WNH stars, the purple line right here, and the WNL stars, which are the dashed blue ones right here. You see that they trace each other very nicely, and they are among the slowest populations. So the flash stars are also supposed to be similar in mass to these guys. And so that's why I'm saying that this dashed orange line, which is the flash stars, is probably biased too much to the high velocities because we're only getting half of these stars. The others are in 30 Dor, and if they haven't escaped from the cluster, they must be going really slow, right? And so this dashed orange line should be further to the left, and therefore, potentially, it would also match the same velocity distribution that we see for the WNH and the WNL stars. So what we're seeing right now is these VMS stars are going pretty slow. And then when we look at these guys, the WN303 stars, which is the dotted red line, and the WC stars, which is the green line, those two are very similar to each other, and they're faster. They're the fastest populations. So we know that the WN303 and the WC stars are lower mass stars. So again, it's kind of like maybe these are supernova things, but you know, there's definitely this mass thing going on. So if the WN303 and the WC stars are going faster, they should be further into the field, right? And that's indeed what we see. WN303s are the farthest into the field of any type except the red supergiants. And the red supergiants, of course, are the most evolved massive type and should have the longest time to get out into the field. So it's quite remarkable to see this WN303 type as isolated as the RSGs. And then the WC stars also are quite far into the field, almost as far as the LBVs and supergiant B bracketes. So that, again, does seem to confirm that they are indeed moving quite fast. So when we look at the more massive types, which are the WNH, the O1F stars, and the WNL stars, we do see that they tend to have pretty slow velocities, all around 20 kilometers per second. And then the WC and the WN303s are going about twice as fast. So what does it all mean? Well, we know that some of these massive stars must be mergers, and it's quite plausible to think that the VMS stars have to include a significant fraction of stars that are actual mass mergers. Which ones they are they, for example, the WNH stars? That has been suggested recently by Lee et al. We also have evidence that maybe the O1F stars, because they clearly have hydrogen in them, could be these helium accretor stars that have been suggested by Richards et al., meaning that they would be mass gainers. So probably these VMS classes consist at least a sum of mass gainers and a sum of mergers. We still have this mass velocity trend where these massive stars are, the VMS stars are going slower than the lower mass counterparts. So maybe there's supernova ejections. This is all, I'm very kind of hesitant to say anything, you know, more concrete here. We're still only just in the process of thinking about these things. But one thing is that since these stars have very short lifetimes, it doesn't give them that much time to be ejected, right? So the dynamical ejection time scale is still quite fast, but it may take on the order of 2 to 3 million years for something like that to happen. So it may be that these that the very massive star classes have indeed been ejected as supernovae or as mergers because they have such short lifetimes. That may not be the case with the WC stars and the WN303 stars. So here are the WC stars. They are quite interesting. So the V magnitude is here, so we're looking at potentially more massive stars up here and mass going down here if you take luminosity as a proxy for mass. This again is the Gaia velocity and proper motion that we see. And if we look only at the single stars for the WC stars, it looks as though there may be a trend here. And so that velocity mass trend, again, is something that you would associate with supernova ejections, which is a little interesting because, as I mentioned, these guys are longer lived because they are lower mass stars, and we may not necessarily expect to see something like that purely. We might expect to see two-steppers or dynamical ejections. The binary WC stars are the orange ones right here. And most of these, first of all, there are more binary WC stars than any other Wolf-Rayet type. So that strongly suggests that the binary mechanism for creating Wolf-Rayet stars applies in the WC case more than the other types. So binaries are probably a good mechanism for creating them, and usually the more massive star, the mass donor, will be the one that blows up first. Notice how there aren't any single stars with masses, with velocities that are out in this region. So that kind of suggests that indeed these binaries do not leave behind the Wolf-Rayet star, right? These binaries are the ones where the WC star is the one that blows up. So it blows up first, and that's exactly what you would normally expect for the binary formation. However, that doesn't explain these guys, right? It means that the single Wolf-Rayet stars, the single WCs, must have been formed through some other mechanism. So I think we're looking at two different mechanisms for creating the WC stars. So in the binaries, we see that the WC star explodes first. It's a stripped mass donor. And that's consistent with the fact that we have a very high binary fraction of these. Those are dynamical ejections because they're binary stars. They're pre-supernova binaries. And then we've got the single ejected stars. So this is where things get very problematic, because that suggests that if they're supernova ejections, their companion exploded first. There is a very special parameter space suggested by Pulse in 1994 where you can actually get the mass gainer to gain so much mass so quickly that it explodes before the donor. Maybe that's what's happening. It's not a very comfortable, because there's quite a few WC stars and this is supposed to be rare, but who knows? I think the takeaway here is that there do seem to be two different methods of creating WC stars. Okay, so for the WN303 stars, those are the ones at the bottom. They're less luminous, so they're fainter. We kind of have the same problem. These are quite interesting. They all appear to be single. There are no binary WN303s that are known, but there's only 10 of them known. They are going very fast, as we saw. These are going at least as fast as the WCs, and they're slow rotators, and most of them are not near 30 Dor, which means that these originate probably from lower mass clusters. So what are they? Again, they could be that strange particular scenario in which I mentioned that Pulse had suggested that the donor is actually the second exploder. They could also be dynamical ejections from small clusters, and that's why they're not going too fast. But how did they get stripped? We don't really know. One thing that we note is that they seem to be quite long-lived. Notice that they're going about the same velocity as the WCs, but when you look at where they are in the field, they are far, far deeper into the field than the WCs, which implies that they live something like 4 to 5 times longer than the WC stars. So that's quite interesting, because they're a rare population, and yet when they do form, they live for a long time. So pretty mysterious, not too sure what those are. Okay, so finally, to end on this, if there are all of these populations out there that are forming hot stripped stars and so forth, we would expect them to show up in the color magnitude diagram. This is a very low metallicity system, NGC 2366. This is Markarian 71, a famous green P analog. My student, Sofia Trushinsky, is doing the photometry of this region right here, region 2, where you can kind of see this is an older region compared to that. And these color magnitude diagrams and Hubble data, for the most part, are beautifully consistent with a 10 million year isochrone. These are T-lusty Indo isochrones that Gustavo Bruce-Wall gave us. Except when you look in the U-B isochrone, you see these guys are not at all consistent with the 10 million year isochrone, the green one. They look like there's a population of hot blue stragglers. Not normal blue stragglers, but ones that only show up when you go to U. Could those be some of these stripped stars or these Wolf-Rayet or whatever kind of stars that we've been looking at that may be evidence of some of this binary activity. Who knows? So I will just leave that with the summary then. For the most part, we think that we have 95% runaways. We have basically a whole bunch of puzzling stuff. I'll just leave it at that for now. Thank you.
Really, really exciting stuff. All right, questions. Anything on this side first, or the guy you always start here? All right, Jeff got his hand.
A beautiful talk. My question is, at the very beginning, you mentioned Lyman continuum radiation from these hot stars. That can have lots of effects that maybe have not been taken into account. For example, the O stars, of course, will be surrounded by H2 regions, and the outer edge of H2 regions is perfect location for forming the next generation of stars. And the radiation from one star on the other can amplitude, increase stripping. So I wonder if you'd comment at all about this Lyman continuum radiation and what roles it might play in the binaries.
Okay, so in binaries, I guess I'm not aware of having Lyman continuum radiation from an O star affecting its neighbor per se. Certainly we have the H2 regions, and for these field stars, the one way that we tried to look at whether an O star actually formed in situ or not was specifically to look at the H2 regions around these. So in the cases where we thought that we did see that, we could see that an H2 region was dense, had the right ionization structure to be ionized by that object, et cetera. And we sometimes even saw these little fingers that you see like in the Eagle Nebula or whatever. So in that sense, the environment did point you to suggesting that maybe 5% of these objects did actually form in situ. So we had those H2 regions. I could imagine that for objects like that had circumstellar material around them, that if you had a binary, that the emission from the circumstellar material could potentially come from the neighbor and not from the star that you think it's coming from. I'm not aware of studies that have actually tried to suggest that that was what was happening regularly with, say, LBVs or something like that. But yes, it's certainly something worth investigating.
Okay, sorry if we just missed this, but I thought you said the binary fraction is higher when it's lower metallicity. Is that right? Why is that?
Why is that? Does anybody else in the room know why? I think it probably just has to do with the star forming conditions, that it's I don't think that it's totally not understood. I think there is a reason for it that I just don't know. Yeah, great question.
So when I think about massive stars, I think about their remnants usually being black holes or neutron stars. Is it known at this point how any of these objects that you talked about very, very clearly, very well, thank you for a wonderful talk, connect with LIGO populations? Like, are some of these classes thought to potentially be more likely to yield ultimately LIGO?
Yes, that is definitely an active area of study. So yes, I think a lot of these subclasses are expected to become gravitational wave progenitors. I have not made the link yet to what our findings about these progenitors do compared to what people are expecting from the LIGO progenitors. But yes, I think that there clearly is going to be some kind of connection there. Yeah.
So I'm curious, can your statistics constrain when dynamical ejections happen? What I'm thinking is that young clusters tend to be much denser, and they evolve, they dissolve. And so your statistics support that point of view that ejections happen at youth and youngest clusters?
Yes, I think there was something that suggested that at one point. Well, for one thing, if we do think that the very massive star types are supernova ejections, then that's telling you that that happened before the things were dynamically ejected. So I think that that is potentially one piece of evidence. There was another thing that occurred to me at some point, not necessarily something I said today, but yes, I think so simulations show that, as one would expect, the time scale for when these ejections happen depends on the density of the cluster, the density and mass of the cluster. I'm just trying to think what that was. There was something that seemed to suggest that dynamical ejections were happening because there was a long time scale involved or something, but I'm afraid it escapes me. But yes, it's something we're looking at. Right. So I think that we're starting to be able to do that, but I've been waiting for the next data release from Gaia before trying to do that, just because, you know, the errors are significant still, and so yeah, I kind of feel like maybe we need to wait until the next data release, but it's certainly kind of the obvious thing to do. Yeah.
Let's thank our speaker again.
Thank you so much.
Thank you so much for joining us. And for all of you, we will see you in the fall. This is the last of our colloquium, so enjoy your summer, the rest of your semester, work hard, and send us speaker suggestions. All right, bye-bye, everybody.